So these notes that we're going to take today are on the electromagnetic spectrum. And so before we get started, everyone should have a copy of the electromagnetic spectrum notes. Look something like this on the front. You're also going to want out today a calculator. So if you don't have a calculator out, if you could take a second to take out a calculator, and I should have some up in the front if anyone needs to borrow one. All right, so we may have heard of electromagnetic waves before and probably have worked with the electromagnetic spectrum at some point in time. And so we're gonna look at that again, but we're also going to dig a little bit deeper. So how can we identify, not just by name, but by wavelengths and frequencies, what specific type of electromagnetic radiation it is that we are looking at? First, what makes an electromagnetic wave different than other waves that we've talked about so far, like sound waves or maybe just a man-made wave, snapping a rope on a string, is that an electromagnetic wave is a combination and then a little more here. So a combination of electrical and magnetic fields that move through space. So a combination of electrical and magnetic fields that move through space. And by space, we don't technically mean outer space, although these types of waves can actually move through a vacuum, such as outer space. But by space, we really just mean the space around us. These electric and magnetic fields, they vibrate perpendicular to each other. So if we look at this diagram here, we have the electric field that's going up or down, and we have the magnetic field that's drawn going side to side. So these vibrations or these field interactions are perpendicular to each other, so at a 90-degree angle, and that's actually what causes it to propagate or to move forward. So as these fields vibrate and interact with each other, it causes the wave to travel in a forward direction. So because these waves move on their own accord, so they move through the energy of their own fields, they don't need energy applied to them in order to move. These specific waves, electromagnetic waves, they don't require a medium to move through. So they don't need something physical to move through. Sound needs something physical to move through, even though we can't, see sound traveling through air. Air is a medium for a sound wave. Or if you are going to generate a wave yourself, you need something tangible, something to touch in order to make that wave. So again, a piece of string, a rope, a slinky. So these waves can move on their own. They don't need something physical to travel through. So these waves can move through outer space. These waves can move through a vacuum. Unlike, again, sound that I mentioned, which need a medium, so there's no sound in outer space. If you ever seen a really great space sci-fi movie and there's an explosion in space, typically it'll be a very quiet explosion. So you don't hear anything crashing, you don't hear anything blowing up, because space is a vacuum, there's a void. There's nothing there for those sound waves to travel through. However, we can get radio waves to travel through outer space. We can get light to travel through outer space. So all these different types of electromagnetic waves can go through a vacuum. So how exactly does this propagation work? So I mentioned that they're vibrating. These two different fields are vibrating at a right angle to each other, and so they are applying a force on each other. And so as they're moving forward, if they do happen to hit a medium, so they do happen to hit something, that electromagnetic wave can still continue to travel forward. So these waves don't just move on their own, but they could actually travel through objects instead of simply just bouncing and reflecting off, again, like a sound wave or a man-made wave might do. So electromagnetic propagation is by definition the absorption and the re-emission of an electromagnetic wave through a medium. So it could be air, it could be something a little more tangible like wood or metals. Electromagnetic waves can actually travel through people as well, for example, X-rays. And so how the wave does this is through vibrations, just like really any other wave. So when an electromagnetic wave reaches an atom, that atom is going to actually, for a split second, it's going to absorb, it's going to take in the energy from the wave, because those electrical and magnetic fields, they do have electrical magnetic energy to them, and it's going to cause them to vibrate. So it absorbs the wave, it vibrates, and then it actually releases the same wave at the same type of frequency. It'll travel to the next atom near it, and the process continues. So it's a continuous process of absorption, re-emission of a specific wave. Again, one we're probably most familiar with is X-rays through people. So those X-rays are literally passing through every individual atom through our body at a very quick, fast rate. Our atoms that are making up our body are literally just vibrating, and we're having that wave travel through us through a series of very quick vibrations within our body until it passes through us. And then if there is another medium, it'll continue to vibrate those particles to continue to move forward. If there isn't, then it can move forward on its own. So we have a variety of different types of waves that are classified as electromagnetic waves. So they have electric magnetic fields to them. And even though they have these electric magnetic fields, they are very different types, different forms of waves. So we have a way to classify them based on certain characteristics. So the electromagnetic spectrum, which you may have heard of and used before, is a diagram used to show the types of electromagnetic waves and electromagnetic waves, we're going to put in parentheses here, radiation, is electromagnetic waves, no matter what form they are classified as a form of radiation, are generally described as being radiation. So generally when we think of radiation, we think of a bad thing. And so some forms of radiation, some forms of electromagnetic waves are harmful, but there's plenty that are not. So the term radiation can get a bad rap because of all the negative forms of it. But just because something is a form of radiation doesn't necessarily mean that it's harmful. But we have different types of electromagnetic waves, or again, radiation, along with their frequencies and wavelengths. Sorry, probably should have given us a little more room here, huh? Along with their frequencies and wavelengths. So these waves are classified based on how high their frequencies are and how long their wavelengths are, which those two concepts are related. So higher frequency means shorter wavelengths or vice versa. Lower frequency means much longer waves. So in our diagram here, we see these exponents. And so that's used to help us to gauge in size how big or small these waves are. And to give you a real life comparison, so we have the size of the wavelength relative to something that we're probably familiar with that's approximately the same size. We have the name of the wave and the range in which these waves lie. So these waves could be a variety of different sets of frequencies. We have down here sources, so some examples of things that make these waves. And then here we have the frequency of the wave in waves per second. So how many wavelengths we have that occur. And then down here, it's a little hard to see, but this says energy. So how much energy that wave has. So this can give you an idea of the harmful forms of radiation. Those that are going to be more harmful are going to be more energetic. So if we look at our numbers and how they trend from left to right, wavelength in meters on this end of the spectrum is the longest. Whereas over here, 10 to the negative 12, these are the shortest, so really tiny wavelengths. So radio waves have the longest wavelength. And in turn, if their waves are really long, they're going to have very low amounts of energy. And they're going to have a relatively low frequency compared to the rest of the wave. So if I look down at frequency, I see on the left side where the wavelength's the longest, the frequency is the smallest. So frequency here is the lowest. 10 to the 6th is still a pretty big number, but if I keep going this way, the exponents do get bigger and bigger and bigger. So if it's a lower frequency, it's less energetic, so the least amount of energy on our one end of the spectrum. So to give you an idea how big these waves can get, these waves can be as long as a soccer field, as long as a house. So they're very big waves. How you're probably most familiar with radio waves are with AM, FM radios. AM stands for amplitude modulation. So when you adjust the amplitude of the wave, that's how we can get different stations that can tune in radio waves. FM radio waves, FM stands for frequency modulation. So you're changing the frequency of the wave in hertz, and your radio stations that you're tuning into are basically kind of coded to what those frequencies are. Moving along the spectrum, we have next up microwaves. And so you're probably most familiar with a microwave coming from a microwave oven. Variety of different types of radars, though, also emit microwaves. And these microwaves can range anywhere from being their wavelengths to being about the width of a baseball to being about the size of this period on a piece of paper. Next up, we have infrared waves, which are about as long as a cell. So a drastic difference in being able to have the wavelength large enough to quote unquote see if we could versus not being able to be seen. Infrared, so body heat, is a form of infrared radiation. And then we have, it's very hard to see, but for being so small, it's very important. This tiny little sliver here is the visible portion of the spectrum. And so the visible light portion of the spectrum is the portion that you can see. And so we generally just call visible light light. But of all these different forms of radiation, there's only one at a particular frequency wavelength that we can actually see. We can't, though, see microwaves traveling through the air around us. We can't see radio waves traveling through the air around us. You don't actually see the X-ray passing through your body, but you turn on a light bulb, you can see the light coming from the light bulb. So this little sliver here is the visible portion of the spectrum. What also makes this little sliver kind of important too is it's at this frequency or after this frequency where our forms of radiation start to become harmful to us. All these forms of radiation to the left of the visible light spectrum are fairly safe forms of radiation. I mean, you actually emit infrared radiation. So these forms of radiation don't hurt you. You have radio waves going around you all the time through radio stations. Your cell phones, to some degree, depending on how old they are, what kind they are emitting waves around in this spectrum here between radio and micro. But after the visible light portion of the spectrum to the right of it, we do get to radiation that becomes progressively harmful because those wavelengths are getting shorter and these frequencies and energies are getting higher. So after ultraviolet radiation, or after, I'm sorry, visible radiation, we have ultraviolet radiation, so UV rays. So a little bit of sun is a good thing, but too much sun, we get a sunburn from UV radiation. After UV radiation, we have X-rays. And X-rays, same thing. If you get an X-ray, a couple times a year, that's absolutely fine. That's not going to cause any damage to your body. But too much X-ray exposure does show a pretty profound link to cancer. And so you may have noticed, if you've ever had an X-ray, that every time you get an X-ray, that X-ray technician never stands in the room with you. They leave the room, or they go into a special spot in the room that's enclosed or sectioned off to prevent themselves from getting exposed to X-rays. Because again, you get an X-ray a couple times a year, go to the dentist, you break your arm, like that's not going to really do anything to you. Kind of like, sunburn here and there. But too many sunburns, or in this case, way too much X-ray exposure, could cause damage to your cells in the long run. And then lastly, we have our gamma rays. And so gamma rays are the shortest wavelength waves, and they have the most energy because they have the highest frequency. So our gamma rays, so this is where we're looking at radioactive material. So these rays being emitted by radioactive isotopes. So overall, as a rule, as our frequency increases, or in short, as our wavelength shortens, gets smaller, the energy of the wave increases. And so we get more energetic as we go from left to right. Come test and exam time, you won't be expected to have all of these waves memorized, but you will be expected to know the two extremes of the spectrum. And then we're going to really focus on visible light. So that is, though, kind of its own separate thing. But you do need to know radio waves, weakest energy, longest wavelength, gamma rays, highest energy, highest frequency, shortest wavelength. So these two extremes are what you'll have to memorize come that time. All right, so that visible light portion of the spectrum, we're going to focus a little bit more here on this particular sheet. So our little sliver can be further broken down into individual separate wavelengths. So generally it's broken down by around like every 150 or so, what's called a nanometer. So a nanometer is 1 × 10⁻⁹ meters. So it's still a very small wavelength. But when you see nanometer, that's our exponent that we're thinking of, 1 times 10 to the negative 9. Now, the speed of light that we can use to calculate different frequencies or wavelengths of light, and actually, since visible light is a form of radiation, all of these other forms of radiation do travel at the same pace. But the speed of light, we use the letter C to represent it. It is a constant. And that value is 3 times 10 to the 8th meters per second. So this is much faster than how fast sound travels through air. Sound only travels at 343 meters per second. To give you an idea how fast the speed of light is in miles, so it's over 186,000 miles a second, not even miles per hour. If we're going into miles per hour, it's over 6 million miles per hour. So very incredibly fast. Comparing speed of light to sound. We're in Michigan. I'm assuming you've been outside or at least close enough to a thunderstorm to where you could see lightning and hear thunder. You may have noticed that unless the storm is really right on top of you, that when you're outside in a thunderstorm, you see lightning before you hear it. And that delay is literally a time delay between the light wave and the sound wave. There's a flash of light, you see the lightning, and then a few seconds later you hear the crackle of thunder. And so that's the difference between how fast those waves can travel or get to your ears. This is significantly faster than how fast that sound wave can get to you. And so, well, it's not the best rule to follow, though. That can give you a good gauge of, too, how far away, the storm is. So if you see the lightning and it takes quite a bit of time until you hear the thunder, then it's probably much farther away from you than if you're getting them, simultaneously. Then it's pretty much right over your head. So visible light being the light form that we can see, the different wavelengths of light that we have is responsible for the different colors that we see or perceive. So you may or may not know, so white light, so when I turn on a light bulb and I see the white light that's coming from the bulb or coming around the room, white light is composed of all the colors in the electromagnetic spectrum. However, if I'm looking at an individual item that has color, the color that I see is the frequency of light that actually gets reflected back to my eyes. So my brain perceives different frequencies of light as being different types of colors. And it's all based on the wavelength of the light. Again, frequency goes with wavelength, so those different wavelengths, those different frequencies represent different colors of light. So violet purple is 400 nanometers. Blue is at 475 nanometers. Green 510, yellow about 570, orange around 590, and red 650. A nice way to remember the order, and probably in reality I probably should have had the order of this flip-flopped. It's good old Roy G. Biv. He may have been taught that to remember the colors of the rainbow. Red, orange, yellow, green, blue, indigo, so kind of blue, purple, and then violet. Another way to recognize the order of the colors on the visible light spectrum, going from longest wavelength to shortest wavelength, is if we look at the forms of radiation outside of the visible light spectrum. So to the left of it, we have infrared. So this side would be the red side. And then we go Roy G. Biv, so we get to violet. And then that takes us then to ultraviolet. Who else going here? Anyways, ultraviolet. So the two extremes on either end can help us to position which side's the longer wavelength and which side is the shortest wavelength. So these values aren't like specific. So they do occur in ranges. So if I have reflected back to my eyes a wavelength that's 572 nanometers, because that's very close to this about 570 value, that would still be perceived as yellow. So these numbers aren't specific. So when you're determining what color it is that you're looking at, you're trying to find the number that's fairly close to these values given here. All right, so as you can imagine, we are going to be doing some math with this electromagnetic spectrum being physics class. And fortunately, we don't have a new equation that we're going to be using. So we're going to use V equals F times lambda for this unit as well. And what also makes this pretty nice too is we have less numbers we got to use because we're always going to use C as our speed because C is a constant. So all these electromagnetic waves are going to travel at this particular speed. So since I know how fast these waves travel, if I know either the frequency or the wavelength of the wave, then I can identify what type of wave it is that I'm looking at. So as a practice problem, so I have an electromagnetic wave with this particular frequency, so 1.5 times 10 to the 11th hertz. So if I know my speed is going to be C here, 3 times 10 to the 8th meters per second. And generally, too, you'll see, and you're more than welcome to use this way. Actually, I'll probably be switching over to this way anyways. But you'll see this written as C equals F times lambda. But my speed is 3 times 10 to the 8th meters per second. F is 1.5 times 10 to the 11 hertz. And I'm looking for how long the wave is, as well as what type of wave it is. So C is F times lambda, and I'm trying to find wavelength here. I can divide both sides by the frequency, keep them balanced. So what I do on one side, I want to do on the other. C over F will give me lambda. So 3 times 10 to the 8th meters per second. Remember, with our calculators, we do need to tell them that if we have something in an exponent or in scientific notation, we got to keep those numbers together. So parentheses or that EE key is going to be important. And 1.5 times 10 to the 11th hertz. So I divide that out. I get 0.002 or 2 times 10 to the negative third meters. So 1, 2, 3. And so it's easier to use these numbers in scientific notation because our diagram has those exponents. So I'm looking for a wave that has its wavelength at 10 to the negative 3 or the frequency at around 10 to the 11 hertz. So looking at my diagram here, so frequency is 10 to the 11, or my wavelength 10 to the negative 3. So this falls along the area of microwaves. So this particular wave that I'm looking at here is likely a microwave. So at this point in time, we're going to pause the video And we're going to have handed out here a half sheet called Analyzing the Electromagnetic Spectrum. So you're going to take some time getting comfortable practicing which form of radiation is going to be on the right or the left side, where it is on the spectrum. And then on the back, some practice problems calculating frequency or wavelength using our speed of light constant. So remember, the constant for the speed of light is going to be c, so it's 3 times 10 to the 8th meters per second. And then you'll also be identifying the waves or color. So you'll want to use this diagram here. So we're going to take a second to pass this out, and then we're going to pause the video, and I'm going to have you work through this, and then we'll go through and correct it. Now, I generally get some questions here with this section. So here you have all these options. You're not picking amongst A, B, C, or D. You're going to actually circle, is it red light or blue light? And then that's one question. Is it microwaves or radio waves that have the longer wavelength? So this will have 4 forms of radiation circled in this section. You're not picking one answer choice from the side here. And our sub does have the keys, so they should be able to help you out, give you a visual of what it is that you're doing if there's still any questions with that. But there should be 4 different things circled through this column, not only one of these answer choices on the side. So we're going to pause the video, and then we'll go over these answers. So everyone at this point should have worked through our Analyzing the Electromagnetic Spectrum. And so now we're going to go over real quick and check what we have circled, just to make sure we're on the right track here. So for this first set, we're circling the forms of radiation that has the longest wavelength. So on my electromagnetic spectrum, I'm circling whatever is on the leftmost side. So whichever is more left is going to be the form of radiation with the longest wavelength. So specifically with my colors, between red light or blue light, so on my spectrum, here's the longest. So red is longer than blue, which is over here towards purple. So red is more left than purple. Microwaves or radio waves. So radio waves are more to the left than microwaves. So radio waves are bigger. Infrared or red light. So red light's going to be in the visible portion. So infrared is more left. And then gamma or UV. So UV is more to the left than gamma. If at any point we need to pause, that's absolutely fine too. Let people catch up. Here we're looking for frequency. So greater frequency. So now I'm looking for which wavelengths are more on the right side of the spectrum. So if I'm going Roy G. Biv, so green is more to the right than yellow. Gamma, higher frequency than X-rays. UV, higher than violet. And then using my pictures at the bottom here, AM, FM radio, FM radio, a little higher than the AM. And 3 here, so each of the following pairs circle the form of the radiation with the least amount of energy. So least energy, lower energy, I'm thinking left side. So red has less energy than blue. Radio waves less than microwaves. Infrared less than red. UV less than gamma. Yellow less than green. X-rays less than gamma. Here I circled a little too fast. Violet less than UV. and AM less than radio, or AM radio less than FM. All right, so then you're going to flip now to the back for yours. Look at our practice problems here. So here we have Springfield's classic rock station broadcasts at a frequency of 102.1 times 10 to the 6 hertz. How long is that radio wave in meters? So looking for length. So we're going to divide both sides by frequency. Get speed over f equals lambda. So 3 times 10 to the 8th over 102.1 times 10 to the 6 gives us 2.9 meters. So that radio wave is 2.9 meters long. You have this work, but not this answer. We might have forgotten to put parentheses around our exponents before we divided. If we don't do that, then our calculator will probably give us this number on top, but it's just going to divide it by this 102.1, not 102.1 times 10 to the 6th. We have a beam of light with a wavelength of 506 times 10 to the 9th meters, and so we want to know the frequency of the light. So speed's always on top. We're going to end up always with lambda or f on the bottom here. So in this case, divide both sides by lambda to give me lambda at the bottom to equal frequency. So speed of light over the wavelength gives me 5.9 times 10 to the 14th hertz. So here I'm asked, what color is that light? So in nanometers, here, I see that 506. So in my diagram, 506 is pretty close to 510. And so if 506 is pretty close to 510, then it means it's going to be whatever color 510 is. So 510 is green. So this is likely light that's getting reflected back to my eyes in the form of green light. Blue light has this frequency, and so we want to find the wavelength of blue light. So speed of light over the frequency gives me 4.3 times 10 to the negative 7. Or if I move my decimal over a couple of places, that give me about 430 nanometers. Lastly, so we have an electromagnetic wave with a frequency of 2.3 times 10 to the 20th hertz. So we want to first find the wavelength and then determine what type of electromagnetic wave it is. So speed of light over the frequency, we get 1.3 times 10 to the negative 12. So that is a bit of a gray area here as to which one, since it's right at the extreme of the spectrum. So since it's at the extreme, it's probably more likely a gamma ray. However, our diagram does have hard X-rays kind of ending at the end there, where gamma rays are starting. And so I would accept hard X-ray too. But we're looking at our exponent, so 10 to the negative 12 up here to help us to figure out where on the spectrum it is that we're looking. So that's it for our notes for the day, as well as, I guess, our practice sheet. If you're still feeling like you're kind of struggling understanding electromagnetic waves, the electromagnetic spectrum, so I do have another YouTube video in Google Classroom that you can watch at your leisure that hopefully might clear up any questions or concerns that you have. Otherwise, you know how to contact me. I hope you all have a nice day, and that's it for our notes.